Today we're going to continue our study of trigonometry by studying the 6 trig functions: sine, cosine, tangent, and their reciprocals, cosecant, secant, and cotangent. You probably remember from last year the definitions of sine, cosine, and tangent as so katoa. The way that we're going to define them today is different, but it's essentially the same thing and get you the same results. So the first one is that sine of theta equals y over r. Now what's the y and what's the r? Let's suppose that we have a point out on a circle. Of course, those coordinates are going to be some x value and some y value. X would be the distance right or left, y would be the distance up or down. So we take our y and divide it by r to get sine of theta. This would just be just like so katoa, with the so being opposite over hypotenuse. This is our theta, that would be our opposite, and that would be our hypotenuse. So we get you the same results. Cosine of theta is defined as x over r, and tangent of theta is y over x. Now, these bottom 3 trig functions are reciprocals of one of the trig functions above it. So for cosecant, which is we wrote it out in the full word form, is spelled like that, be the reciprocal of sine, which is y over r. Next up, secant, SEC, not the Southeastern Conference, but the trig function. Secant is spelled like that, and it's the reciprocal of cosine. So that's r over x. Next up, cotangent, spelled like tangent, but with a CO at the beginning, is the reciprocal of tangent, and that is x over y. Next up, we're asked to find the exact values for a trig function at a particular angle. Now, I've got some coordinate grids or coordinate planes there. Now, when we do these problems, we're going to use that concept of reference angles that we studied in the last lesson. And we're also going to use a couple of reference triangles that you've probably studied in the past. And those are the 30-60-90 triangle and the 45-45-90 triangle. We've got a 30, 60, 90 and a 45, 45, 90 here. 45, 45. All right, so for 30, 60, 90 triangle, one basic form of a 30, 60, 90 triangle has a side length of 1 unit, root 3 units, 2 units. The 1 unit long side is always found across from the 30-degree angle, and the root 3 side is found across from the 60, and the 2 side is found across from the right angle. For 45, 45, 90, one basic example of those has side lengths of 1 unit across from the 45s, and a root 2 length for the hypotenuse across from the right angle. So we're going to use these along with the reference angle concept from yesterday. All right, so cosine of 2 pi over 3. Start by drawing the angle 2 pi over 3. Now, 2 pi over 3, if you convert that into degrees, is 120 degrees. Put a initial side here. Terminal side would put us in quadrant 2 right there. So then we think, what's the reference angle for 120 degrees? That's going to be 60 degrees. So put a little 60 in here. Then think of this as a triangle going down from your terminal side. And then we've got 60-degree angle here, and this one is a 30 in there. Let me try to zoom in on this a little bit for you. That one's a little sloppy, but, well, actually, why not erase it before you do a little better one? Make this thin. So this would be 60 degrees in here. Drop down, and we've got 30 degrees up in there. So 60 degrees, 30 degrees, and 90 degrees. So we've got a 30, 60, 90 triangle. Across from the 30 degree side is 1 unit. That thickness is bothering me. This one is too thick, this one is too thin, and this one hopefully is just right. Across from the 60 degrees, we'll have root 3, and across from the hypotenuse we've got 2. So now, we ask ourselves, what is the cosine of 2 pi over 3? So let's remember that cosine is x over r. So the x value for this reference triangle is going to be x over r. Now, for this 1 unit side, notice that we had to go to the left along the x-axis. When you go along the x-axis to the left, that value is going to be negative. This y value will be positive because we're going up that many units. Last, for these reference triangles, the hypotenuse is always positive, no matter whether we go up, down, left, or right. So for the cosine of 2 pi over 3, we take that x, which is negative 1, and then we put that over the r, which was 2. So the cosine of 2 pi over 3 is negative 1/2. Next one, negative 7 pi over 4. Convert that into degrees, and we have negative 315 degrees. So we'll start at our initial side. We go negative clockwise all the way into quadrant 1. It's where we would find negative 315 degrees. So this would be 45 degrees in this space that I'm trying to hover in. And so our reference angle down in here would be 45 degrees. So then we take that reference angle, change the color. We drop down a triangle down to the x-axis. Got a 45 degree, meaning that that's 45 in there. And so our x would be 1, our y would be 1, and our hypotenuse would be root 2. We just use this reference triangle over on the right. So tangent is, as we saw, y over x. So that would be 1 over 1, which is 1. Last, the secant of 7 pi over 6. So we'll start at the, again, positive x-axis. That's where our initial side is. Terminal side, we'll go 210 degrees in a counterclockwise fashion. So we go past 90, past 180. We go 30 degrees past 180 to get our 210 degree angle. When we make the reference triangle, we go to the nearest x-axis. This would be a reference triangle here. So that gives us a 30 degree in there, 60 degree there, and a right angle. So we use the side lengths from our first reference triangle. The y value, since it's going down, is negative. The x value, since it's going left, is also negative. And then the hypotenuse is always positive. Now, secant. Secant is r over x. R is 2. X is negative. That's a negative symbol there. Root 3. Now we need to change this format because we've got a square root in the denominator. So let's multiply this by root 3 over root 3. and we're going to have negative 2 root 3 all over 3. Next up, quadrantal angles. A quadrantal angle is an angle for which you can't draw a reference triangle. These are an angle which has a terminal side, an angle with a terminal side on an axis. If you try drawing a triangle, you'll find out that you wouldn't be able to. It would just basically be a stick, and you can't draw a triangle with it. So what we need to do for quadrantal angles is know a little something about the graphs of the sine, the cosine, and the tangent functions. So for a sine function, let's mark our axis at multiples of 90 degrees. This would be 90, 180, 270, and 360 degrees. I'm going to list these in degrees, but of course you could do it in radians too. Often you'd see it in radians. Negative 180, negative 270, negative 360. Alright, and the y-axis, we're going to go from 1 to negative 1. Now at this point, there's a class coming in. You may have just heard that bell, so I'm going to pause the video for a moment, hopefully get back with you in a little while. The sine graph starts at the origin, and at 90 degrees it goes up to 1, at 180 degrees it drops to 0, at 270 degrees it goes to negative 1, and at 360 it's back up at 0. And so in between it does a curve, something like this. And then it repeats that pattern as you go forward to the right. You go back to the left, it basically repeats it, but the opposite way. So it goes down to negative 1, up to 0, up to 1, and then back down to 0, and then it repeats the same sort of pattern. Now, a cosine graph is very similar to the sine graph. The only real difference is where it starts. Instead of starting at 0, 0, you can think of it starting at the point 0, 1. It goes down to 0, then down to negative 1, up to 0, up to positive 1. And does that same sort of curve, sort of wave that's going up and down. And we'll put in these points here. We'll be studying more about trig graphs later this year. And so you can see that the cosine graph is essentially the sine graph, but shifted over by 90 degrees. The tangent graph looks much different than either of them. Tangent graph has a couple asymptotes. These asymptotes are at positive 90 degrees and negative 90 degrees. They're vertical asymptotes. It's rather hard to draw with this stylus that I have. You get the idea. So we have vertical asymptotes at 90 degrees, and negative 90 degrees. And in between, we essentially have a single curve, goes through the origin, and at 45 degrees, it hits 1. At negative 45 degrees, it hits negative 1. And between it does a curve which approaches that asymptote but never reaches it. Does the same sort of thing over here. goes to the point negative